All right, so thank you again. It's great to be here in person with so many people. Congratulations to the organizers. I think this is a great occasion, and I don't want to bother you too much with MLIR tech details and like a landscape of everything that exists, that has existed and will exist. I just want to highlight a few interesting, I think, challenges that are still that maybe MLIR was aimed to solve, but maybe not necessarily succeeded in that respect. And hopefully also bring some light on what it can be as a tool for research, not only for engineering, because as you know, this is primarily a type of infrastructure that people design for building large-scale compiler infrastructure. But as a research tool, how valuable is it? But then I guess the next presentations will be even more interesting for that matter. So first question is, no, I lost the focus here. Yes. First question is, what are you guys doing here? I mean, this is this is very strange. I mean, everything is happening right now in California. So, I mean, actually, last week we had the LLVM dev meeting, and there are many more events, and there's also an Open XLA workshop organized this week. I'm also supposed to be there for other reasons, but thanks to the organizers planning things early enough, so that was possible. But let me seriously highlight in particular the workshop that was organized by my colleague Alex Zinenko on the first day of the LLVM dev meeting. So there have been 16 presentations, about 150 people at the best times, covering many different topics, some research, some engineering with MLIR. So the slides and recordings are not yet online, but for recordings, it typically takes a month for the LLVM organizers to do that, but the slides should be there shortly. And there was also a very interesting ML-guided compiler optimization in LLVM kind of workshop discussion. I don't know exactly what part of the material will be available online, and many relevant presentations in the dev meeting itself. So lots of things are happening, and I just want to maybe give a little bit of recap of why people are excited by this technology, and again, how it can be interesting for research. So the first question I'm looking into is how compilers can contribute to ML, and that's part of the excitement about compilers in the last, let's say, 10 years or so, maybe 8 years, driven by the needs of machine learning. And then I will go the other way around and discuss about some challenges in ML for compilers. So basically, what people call compilers in the machine learning space are typically tensor compilers at large, whatever it means, whatever tensor means. I don't want to get into details of that. And I just want to highlight two examples, one at high level, one at low level, which is JAX and XLA, because they are very different types of compilers. So many of you already know that. I just want to briefly mention these different, like this landscape. So JAX, just like PyTorch or TensorFlow, Keras, there are many frameworks, typically Python-based, for machine learning, for differentiable programming at large, beyond the plain machine learning like neural networks. It looks like functional programming on arrays, on functional arrays. So everything is a value. Everything can be soft, can be made soft, differentiable for training purposes. And you have primitives that are essentially low-level operations implemented efficiently on specific hardware. For example, the NumPy library, which is the basis for the JAX framework, the NP dot syntax here, has a bunch of numerical functions like dot products, matrix multiplication, hyperbolic tangent, etc., that do what they are supposed to do on tensors of variable rank and shapes. And those functions can be organized, those primitives can be organized into more complex components that are differentiable, parallelizable, can be distributed, can be organized into modules that can be just-in-time compiled. These are all what JAX people call transforms, or like high-level transformations, basically, by source-to-source, or let's say high-level rewrites of the sum IR, which is very close to the sum. So this family of ML compilers, of tensor compilers, is not really dealing with the low-level operations like dot, hyperbolic tangent, etc. It's just dealing with orchestrating all these operations, typically in parallel, sometimes very, very large scale, like tens of thousands of nodes and maybe even more accelerators. And with the JIT compilation aspect, the differentiation, like automatic differentiation of the functions that need to be trained, backpropagated, etc. So this is very popular, and this typically works because underneath there is another compiler which does the heavy lifting for performance. Okay, so it's great to have these high-level transformations, but you need something that actually targets your hardware, like a GPU or TPU. And in the JAX landscape, this compiler is called XLA, which originated from TensorFlow, but now is an independent project. By the way, it's called OpenXLA now because it's a community-first project, but it's still the large parts of XLA inside and also MLIR. And this is what's supposed to give you the best possible performance. Even I mean, when you say JIT in the JAX or a context, or in PyTorch when you trace and when you compile some functions, it's the same thing. You get this type of compilation happening underneath. So this is very interesting because you can do high-level transformations, as I said, completely independently, like it's very modular from whatever happens underneath when you compile on a given machine. The main problem is that when you do, like, for example, trace compilation at high level, you get some context to be optimized, but only at the last minute. So it's a domain-specific environment where the shapes can be specialized, the size of the tensors, the ranks of the tensors, the data types, etc., which is great because you can take advantage of it for getting the last bit of performance, except that you typically know that at the very last moment. So only when you actually have traced through some control flow, you figure out, oh, this is the path of execution. These are the constants that will define the shapes of the tensors, and eventually you know how to generate good code for it. But you don't have much time for this if you do it in a just-in-time mode. So this is interesting because it puts a lot of constraints on what the domain-specific compiler underneath, like XLA, can do or should do. And XLA itself, as I said, it can be used both as a JIT compiler and an ahead-of-time compiler. It's targeting a very, I'd say, restricted but not that small set of operations. Actually, too many, I think, to be reasonable, to be scalable. A few more than they are called HLOs, but they are the 100+ operations that you find in conventional neural networks typically, and a few more like Cholesky factorization and things like this. And it knows very well how to generate good code for these apps, or it knows very well how to code a library that already does it for you. So, and actually, that's a little bit of a disappointment. If you look at what XLA does at high level, it understands the trace that has been isolated by the ML framework, like JAX. It does like graph transformations at that level, for example, like typical different forms of fusion to save data transfers, going back and forth to main memory or global memory in the GPU, etc. It does tiling, it does vectorization, all kinds of so-called loop transformations, but it doesn't necessarily do that for all the operations that you are dealing with. And for example, if you are not like a first-class architecture, like hardware target of XLA, most of the time, in fact, the execution is going to be, you're going to spend time on numerical libraries that have been provided by third parties, like Intel, MKL, this type of, or QDNN for NVIDIA. So there is a little bit of a tension here about what part of the computational load is actually happening in generated code, and what part of it is coming from external libraries. And in effect, people call this a tensor compiler, like backend in a way, but it's more like a library API. It's more like a way to bind a few operations that have been fused in a cluster to existing library implementations, or to predefined templates, predefined way of generating specialized code for these fused operations. So it's not exactly the ideal scenario for a domain-specific compiler. I just want to mention that JAX is not only for ML, and the ML frameworks in general, PyTorch as well, have been used a lot for all kinds of applications. PyTorch is being used as more like almost as MPI these days. So you get high performance computing research. They don't want to look at like communication libraries, of course MPI, with collectives, or Nickel for CUDA. They just say, okay, it's PyTorch. Underneath there are some communication libraries. I don't want to know how it works. So same thing with JAX. And it's, of course, it's better than just a communication library because it also gives you all these transforms, like automatic differentiation, JIT compilation, etc. So there are a bunch of, I mean, this was the state of the art like 2 years ago. So there are more research I have not listed here, but there are very diverse, like numerical simulation, physics, control, like model predictive control applications of these frameworks. And actually, if you are doing HPC today, you should always question whether it fits in. It's actually sufficiently simple, let's say, to match the expressiveness of those frameworks. So the other way around, please interrupt if you have questions or if you have comments or disagree or whatever. Yes.
Maybe a question on the traces. So when you start working from traces, does it mean that you know from the traces what the traces are repeated all the time?
Yes, it's typically a loop that's being unrolled or control flow paths that are essentially traced, like literally, like in a trace compiler for a dynamic language, and it's hopefully going to be repeated. Otherwise, you're wasting the time of this compilation. That's the advantage of controlling explicitly in the language. That's a little bit different from PyTorch, but the fact that you can PyTorch 2 actually does the same now. You can decide basically as an expert performance engineer whether it's worth or not to compile. Yeah, so that's, of course, if you are in a kind of production environment, you may completely get rid of this JIT compilation. You can cache the JIT compiled code and actually mimic ahead of time compilation. So the other way around is just as exciting, or maybe even more exciting. And it's not new. So I don't know how many of you were born when iterative optimization was a keyword, or feedback-directed profile-guided optimizations, PGO. I see a few faces here. We were definitely there at that time. Yeah. So it's not that long ago. It's like late 90s. It's still there, okay? Except that the technology behind it, now it's called autotuning. Nicer word, actually. Has made a lot of progress as well. So it's not only, let's say, feedback from actual execution. There is a lot of modeling going on, like surrogate functions for cost models, for performance models, search meta heuristics that try to learn through the search, through the exploration of the search. It can be very basic, like just tuning optimization flags. Should I turn inlining or not? So what's the threshold for the size of a loop? For the loop to be unrolled, this type of things. Or it can be much more advanced. I'm going to give an example later, but like how do I make classical compiler optimization like register allocation be operated via some kind of search or synthesis algorithm, or using machine learning for deciding what registers to spill, how to prioritize different optimization strategies, etc. So this is very active. Just to give you an example, again, in the context of JAX and XLA, there was this paper at PAC 2 years back by colleagues showing how you can make this type of auto-tuning techniques friendly to a very complex production environment happening like lifelong. Like actually, that was the original name of LLVM. So it's something that happens while the code is being developed, tested, deployed, used in production, and through all the lifetime of some software engineering projects that use XLA underneath. How do you actually collect data? How do you learn new performance models? How do you search for the best combination of flags? It's kind of very basic search space, just optimization flags, but how do you actually make that compatible with production environments, including the implementation stages, regression tests, integration tests, etc. So this is very interesting kind of methodological aspect that some people have been had the vision of, like Gregor Efferson, for example, some time back. But it exists, like it runs in production. I'm going to talk about something a bit more internal to compilers, because I think here you're more interested in building things than maybe orchestrating large-scale production systems. And this is some work we are doing in collaboration between 3 Googlers and from different parts of Google, and colleagues from IIT Hyderabad. Some of you know Ramakrishna Badrasta has been spending some time in Orsay, in Saclay. And this is about like also methodological work, but how to actually open the box of the compiler to make this type of auto-tuning research more powerful. So, and also more efficient. So the goal here is not only to tune flags, but to say, okay, we want to have ML entering compilers, but very deeply, like from the bottom up. This RL for real paper earlier this year at CC was all about using very aggressive reinforcement learning techniques like state-of-the-art graph neural networks, cost models, representation learning. That means actually extracting representation, the LLVM IR, and making actually the MIR, the hardware like assembly level model, extracting features automatically from it, not doing any feature engineering, and in the loop of spilling registers, of coloring registers, of the different heuristics that take place. Actually, 3 out of the 4 steps of register allocation use this RL framework to improve register allocation. And other techniques like phase ordering, other classical problems, loop distribution, etc., have been addressed with similar approaches. The main problem here is that when you open the box of the compiler, first of all, you have to be able to do it. You need to extract the information. So LLVM is not that bad for that because it lets you serialize the IR more or less at every possible step of the compilation. At worst, you can just print strings and parse the strings again in Python. But when you do that, okay, you have the information. You still need to be able to process it. In Python, it can be super slow. For example, they were using RPC calls initially, and that was like 100x overhead. And not only the RPC call mechanism itself is slow, but also you have to re-inject the decisions inside the compiler optimization. For every register spilling decision, for example, you may have to say, let's get some results from a neural network, in this case, even a graph neural network, to say, oh, this is the highest priority register to be value to be spilled as like the result of sorting some probabilities outside of a high dimensional vector. So it's very expensive. Actually, 100x is already the result of some serious optimizations there. And this is 100x over the full compilation time. So not just register allocation.
And what is the gain?
So the gain is pretty good actually. It's, it depends, but it can be on some benchmarks. It can be like, for example, in presence of large basic blocks where the heuristics are not very good, you can get like 20%, 15%. For register allocation, it's sometimes it's just like 2-3%, which is much more standard register allocation benefit, but occasionally it can be nice. And sometimes it's very bad. I mean, not sure if it's because of ML or because of the machine. So there are many ways of doing that better. So it's, yeah, we can do it. It's possible. Sometimes it wins something. So I should have said that. It's obvious. Otherwise the paper would not be accepted. But how do you do it, really? So, and I think that's the large part of the message in my talk is how do you make things possible and reasonably efficient, especially if you're interested in transferring some of your research to the community or to production systems. Then the questions are really not, and the answers are really not clear at this point. So we used the gRPC at the beginning. Other colleagues at Google independently had this project called MLGo, which has landed into LLVM 14 the first time for inlining, and now register allocation as well, but only the eviction step of register allocation. I don't go into details. You can ask me questions later. They used more like ad hoc, let's say IPC, like pipes, like Unix pipes, to connect LLVM with an external model. They also use TensorFlow C API. So some ML frameworks have the ability to serialize, like to dump so-called saved model that in executable form. So just get function calls like in .o files that will actually run the model on actual data. So you think of it as, I mean, we are in 2023, so we are reinventing ABIs to actually call functions on data and get results. That's, wow. So after so many years of doing Python meta programming injection and stuff like that, people rediscovered that you can actually call a C function or just and get some results out of it. So this is great. So there are actually tools that do it automatically for you, of course, because it starts from Python meta programming. But that exists at the cost of slightly specializing the model, because you cannot do random Python hacks, of course, if you want that to happen. Otherwise, you're back into compiling Python. There is also the ONX execution environment, which is both an execution like a runtime and also a standard like for interoperability among frameworks that originated from Microsoft and Facebook, and it's pretty good as well. It's not complete, so there are some ops that are missing, but it's efficient and it gives a good coverage of practical like traditional popular models. And the question is, okay, what's best if you want to integrate ML inside the compiler? And so we are conducting this story this investigation as we speak. We basically tried every possible combination of like training, inference, fine-grained decisions like register allocation, coarser grain stuff like pass ordering, and see how the different methodologies for communication fare in these different scenarios. And I don't want to go into all the details, of course, but there was a presentation last week at one of these workshops I mentioned. In general, it's all about how you serialize, do you need to actually communicate across processes or not? Or is it just in-process function call, as I mentioned earlier? And sometimes your mileage may vary depending on how you do it and depending on the scenario. So RPC involves a lot of code generation, but eventually you get a very specialized serialization and communication infrastructure. I'm not spending time on this. You can use just plain function calls, as I mentioned, when it's possible, depending on the framework. But if you do JAX, then you cannot use TensorFlow. So there are a few choices in terms of velocity and how plug and play the technique can be. And there is this ONNX kind of potentially ideal scenario where you develop the model in whatever framework, convert it into this intention format, and eventually serialize it to a C source file, C++ source file that you compile and link the usual way. Again, it has to play by the rules of ONNX. Not everything is supported there. But that's one of the approaches. And eventually, so I have this table showing that if depending on whether you are in a kind of multi-threaded mode or not, like if you want to run multiple, compile multiple functions in parallel, then you're not going to do it with pipes or gRPC, but you can do it easily, like single like in process, multiple threads using ONNX or TensorFlow, because these are just like thread-safe function calls. If you want to do distributed training at scale, then only the RPC mechanism works. So there's a cost to it, but it's scalable. Okay, this is kind of obvious. If you want like robustness, meaning you're not going to, that maybe is not something that you think about in research, but if you're not going to have compilation errors or crashes in one of the processes running out of memory, or I don't know, out of memory errors actually pretty frequent when you do training, these robustness questions arise. So depending on the mechanism, you are going to build a system that's much more resilient to faults. Even on a single node, this is important. And actually compiler crashes are probably the most frustrating source of these faults, because as soon as you start doing ML and stress the compiler in directions it was not necessarily tested with, you're actually fuzzing the compiler and you get a lot of bugs. So that's not something you think about right at the beginning, but almost immediately when you do these type of things, especially when you do it at fine grain, you get into a lot of bugs. So you need a framework that's capable of interacting between the ML system and the compiler at fine grain and reacting to bugs, at least not spending a huge amount of time. Oh, I'm actually compiling forever. There is an infinite loop somewhere, etc. So you have to take care of all these scenarios. And of course, framework independence is also important if you do research. So everyone should use JAX, but unfortunately not everyone uses JAX. So that's it. So performance is there. I'm stating that. You can ask me for the slides will be online, I guess, after that. So there are lots of benefits of training with very specialized models like pipes without just plain bit streams, no serialization through any JSON format or whatever. This is kind of obvious, just showing that it does make a difference. And maybe the most important take out of this is that any communication mechanism is less efficient than no communication at all. So if you just do ONNX, you don't get any overhead. So you just do in-memory communication between the compiler IR and the model. Everything else, when the size of the vectors you're communicating, you're exchanging grow, there will be a little bit of a cost, but it's not necessarily ridiculously large. Okay, so that's just synthetic data, just exploring how the size of the data you're communicating between the compiler and the ML framework influences execution time, and it's as expected, basically, but it's not ridiculously large if you do anything that's a little bit optimized. Okay, so I'm just going to stop there on the ML for compilers part. There are many other projects like integration with reinforcement learning frameworks like CompilerGym, PolyGym, etc. There is more work also on making this native interface, as you've seen, ONNX is quite efficient, more streamlined for different frameworks, for JAX and PyTorch, for example. But this is still work in progress, and I think, as I said at the beginning, this is an old research area. but it's not necessarily. I think we have only scratched the surface, basically, because until recently, people were not even doing any such thing. They're just like tuning flags, tuning existing interfaces. So there are lessons for compiler construction. One of them is how do you build these communication mechanisms, but there are maybe more profound lessons on how do you make the IR amenable to this type of research. So, for example, as I was saying at the beginning, if you want to learn representations from the code, not necessarily through manually engineered features, oh, I know maybe the number of instructions in the loop is going to be important if I need to enroll the loop. Yeah, maybe. But you don't want to do that. You just want to use ML techniques to learn these things automatically. What is the right way of engineering a compiler IR? And of course, I don't have the answer, but I have some maybe this actually philosophical, so some insights about what could be an interesting approach. And of course, MLIR has many of the clues to that. Okay, so the main like generic meta answer is that you don't want to decide too early what's going to be your flow of abstractions. So how do you refine step by step from the source language or domain specific language down to some lower level abstraction or just binary code? You want to let the compiler engineer revise these choices over time. So basically, we are not building a compiler anymore. When we do this type of research, we are building components that will let you reorganize the flow of the compiler at will. So it's not free, it takes some engineering, but be able to reorganize, for example, what do you do first? Which abstractions are going to live together? Do I want to think in terms of loops, like for polyhedral compilers and raise abstractions to nice fine forms? Or do I want to think in terms of more domain-specific and maybe ad hoc tensor algebraic operations? They are less expressive than loops, but much easier to reason with. Do I want to see like the low-level control flow with branches and go-tos and stuff, or do I prefer to keep structure at higher level? I mean, all these questions are typically hardwired in the compiler design, whatever compiler you pick, and they have to be because the compiler has to do something at some point. But we want to make it easy to change your mind. So basically, explore different ways of abstracting the information at the right level, so that you can do research with it and figure out what's best to be done. For example, using ML to decide what's best to be done. And I'm not going to tell you what MLIR is. I think everyone knows about it. Just recall that it's open source since the mid of 2019, and you should not be there. Again, I'm not giving any sensible talk here. I'm just trying to move things around, just hand waving. But there was a great talk last week by Alex saying what MLIR is not. And again, the slides are not there yet, but they will be very soon. As I just said, MLIR is not a compiler. MLIR is infrastructure to make it easy to build compilers, do research with compilers, and maybe most challengingly, do things that are future-proof. So not necessarily take early decisions and then be stuck with those early decisions, but actually revise those decisions over time. Once again, that should be available very soon. So I don't have time, I think, for even showing examples of what MLIR looks like. I don't know how many of you have never heard about like operations, regions, blocks in MLIR. In the interest of time, I'm skipping those slides, but if you care about, we can discuss more like offline. Maybe the most important part of MLIR is not its syntax, which is LLVM inspired and very verbose, just like most intermediate representations, but it's the fact that it has built-in concepts that are not just syntax. And that's something that I've seen people arguing about, especially in programming language spheres, whether this is just an XML or JSON of compiler construction, nice syntax for writing commonly used patterns in compilers, or is it actually semantically interesting? So is there some backbone in the concepts behind MLIR that carries semantics? And the answer is yes. It's not necessarily a lot, because if it was too rich, like too prescriptive, you would not have this flexibility I was talking about. So it's kind of trade-off. It's parsimonious in a way. So we try to bring in some concepts that have been universally accepted in compiler construction, like values, like SSA, functional semantics, as you wish, like structural nesting, and decoupling the meaning from the types or traits of some operations. So being able to say, this is the type of computation I'm dealing with, but it's going to be instantiated on different data types. It's going to have this type of like instance-specific derivations, like attributes, just like tags, basically to carry additional semantics, and ways to build generic infrastructure around it through interfaces. So that's, I think, what you should remember about the design. Is not just syntax, it's both software engineering principles and a little bit of semantics that's universally accepted as a good practice. It's designed for the long term, for use, and this is the syntax, and I don't want to see it. Another part of the design that's important is this notion of dialect. That means at least three different things. It's a way to, it's a module system for software engineering applied to compilers in the MLIR infrastructure. So you can group in a given module different operations, different types, and different attributes. Specialize them for your specific domain, but it's also a way to compose those dialects. So as any module system, you have a means to let multiple of these abstractions live together. You can decide that some operations are going to live with other operations. For example, you can have LLVM instructions, and at the same time, more hardware-specific instructions like NVIDIA, like GPU-specific instructions, or higher-level loops that remain that actually live in your compilation unit, in your function, at the same time as low-level LLVM instructions. So, for example, you don't have to decide, because you're using LLVM IR, to only use control flow and low-level branches. You can have both structured loops with nesting structure that's explicit, and inside basic blocks that contain LLVM IR, or even regions that have LLVM control flow graphs in the middle of the function. So that, as I was saying earlier, if you want to retain this ability to change your mind, to redesign your flow, this is absolutely essential. Having multiple abstractions live together, typically by importing and composing multiple deltas. So here, what I was saying about semantics falls apart. That's one of the failures, I think, in the design, because we came up with these principles without actually sorting out the difficult semantics problems. We have no clue what's sound and what's not. Okay? So you can bring operations. The examples I was telling you before work well. Yes, you can nest LLVM IR control flow inside functions, inside regions, but you can do all kinds of things that don't make any sense as well. And there is nothing that prevents you from doing that except compiler errors, a little bit of testing, and like unit testing that will tell you, no, this is not possible, this is not supported, but this is trial and error. And if you're not happy, maybe you're right. Maybe there is some ability to compose dialects that was not designed yet, or even thought of, but you have to do it yourself, and then argue for upstreaming it in the project as well. Okay, so this is kind of a weak point, I would say. Yes, it's super expressive, but it does what it does, in a tree. Many research projects based on MLIR. I want to just give a list, but not go into detail. Some people are interested in front ends for MLIR. That some people even complain, that was one of the presentations last week, that it doesn't make any sense to have a framework like that without like first-class citizens in terms of programming languages supported by the framework. I'm not quite sure. I think it's great. It would be nice to have a C++ front-end or Rust front-end or whatever for MLIR, but this is not the point, because it's not a compiler. So if we had such a thing, that would enhance ease of use. So people could start playing with it, plugging their optimization passes and changing things underneath. But at the same time, it may kind of hardwire the way of using the abstractions. And some projects have been successful in the ML space using MLIR in a very specific way, like the Erie compiler, for example. But it's just one way of replicating the LLVM story. You have this kind of black box called op that does all kinds of things, and there are flags. Good, but that's not necessarily what you want. Okay? So that's one way of exploiting the framework, but not necessarily the only way. And there are many kinds of research you can do aside from front-end languages. Like differentiable reactive programming is some personal excitement I have working with Dumitru Potop at INRIA on bringing synchronous languages into the ML space. And we have published something on using MLIR for that, but also doing it at a higher level, and automatic differentiation, etc. So the Enzyme project you may have heard about, if you do automatic differentiation, this is now moving into MLIR. So it has multiple levels of abstraction. It's not just LLVM anymore. It can be extensible, etc. Okay, so maybe I have to choose, depending on your interest. So maybe let me pause for questions, and then depending on questions, I decide whether I talk more about performance or more about kind of futuristic things.
I have a question from Zoom. Can you hear me well?
Yeah, go ahead. Yes, I can hear you.
Yeah. So you say MLIR is not a compiler. So I'd like to, if you could elaborate more on that. So here is my train of thoughts. I understand you're saying that MLIR, it is a framework to explore different abstractions, but at some point when you are happy with it, you may want to generate a compiler as well. So it is also part of a compiler.
It's
right?
part of it. I cannot disagree with that.
Okay. Then like the question of having a front end also makes sense if you think that in the end okay.
No, this is actually great. I mean, there are multiple projects working on MLIR frontends. I think all of these are absolutely superb initiatives because they dramatically increase the reach and interest in the platform. I'm just saying that MLIR remains interesting even without those things. I'm just saying that. Even without a fixed flow black box compiler or frontend, it's already something people have been using. Maybe not to the full extent of its capabilities. So a lot of frameworks are using MLIR somewhere for converting one graph format to another graph format, for standardizing representations, etc. Even for low-level code generation. As I mentioned, for NVIDIA GPUs, if you want to bridge like hardware-specific extensions with the rest of LLVM, it's super convenient. If you want to do vector abstractions in a generic way, and you don't want to generate low-level vector intrinsics, you can use the higher-level vector abstractions of MLIR, etc. But it's even better if people build real things with it. I agree. I mean, like full end-to-end flows with it. But without, it's still useful.
Mm-hmm. And then a question related to that then is like, I have the feeling like if we want to use MLIR with traditional like C-like languages, you lose a lot of the power without having the possibility of lifting the abstractions, no?
That's
so
right.
is it part of the front end to like enable this kind of lifting?
Yes, exactly. So the Polyguys project was initially exactly meant at exploring this question. Is it relevant at all? Can we start from C++? Actually, not C in that case. C++ is more interesting because you have the type system with templates, etc., that brings a lot of potential semantics at the source level that's typically lost later in expansion of Clang to LLVM. So they demonstrated that you can recover lots of structure either by reconstructing it, like lifting it from LLVM, but before doing any transformation, or directly from the expansion of the C++ syntax trees. And yes, so that's a real question. There is potential. Whether it actually makes sense at all, I would typically, for example, maybe Ronan and others have experience with like C++ embedded DSLs. It's not very clear that it brings a benefit right now compared to writing more like embedded DSL using complete metaprogramming, using more like ad hoc C++ specific ways of doing things. Same thing for Python. It's not very clear that redoing JAX using MLIR at high level for these transforms, these trace compilation, etc. It's not clear that it makes sense because it's not even, I mean, yes, you can do it in Python. I didn't mention, but there is completely feature complete. There's feature complete set of bindings for building, traversing, pattern matching, the IR, etc. in Python. But does it make any sense? I mean, compared to a much more lightweight implementation in Python? So I think these are real questions. Whether you want something more idiomatic in the language or something more generic in a framework like MLIR.
Thank you.
So I don't know what's the status of SYCL with MLIR.
Yeah, actually Intel is developing a MLIR branch of SYCL, and I'm studying it to see how it can be extended for handle this kind of stuff.
But yeah, the outcome is not open. And generally, the outcome of such projects is only in the long term when you want to reuse efforts across multiple targets, multiple source languages, multiple like cycle of development. So that's a question for research as well. Because if you do research with MLIR, yes, you can benefit from everything that exists, but it's also a chicken and egg problem. So if there is a rich enough ecosystem, then you can benefit from it. So some teams have students that have been training over multiple generations of students to be super effective at getting into it, being productive with it, contributing, etc. And then they can take advantage of it. But there is a price to pay. So you can take advantage of all this ecosystem, all these things that exist, but it's also a learning curve. It's also a barrier. There is also a barrier of entry. So maybe just briefly about performance. Another thing.
Question from Pierre.
Oui, hello, Albert Sequin-Pierre from Grenoble. I have a question because I don't see exactly what are the. Of course, we are speaking only about an intermediate representation, but behind you, for all intermediate representation, you have an idea of the model of the architecture which is behind. So what I don't see exactly where is the limitation, or what is the solution that you have in this kind of. So I presume that you have, of course, a Goldman style of machine with instruction, but at some point you have difficulties because when we use the GPU, you have to map the data, so you have to deal with data mapping. You speak about communication, which is also in the loop. So maybe it's maybe you will talk about it in the following slide. What is the limitation?
Yeah, it depends. It's a great question. So it depends whether you're taking the MLIR point of view or the user of MLIR point of view. So from the point of view of MLIR, there is no predefined vision of what the target hardware is. Definitely not von Neumann. So the fact that we have SSA is just because it makes sense from a computational perspective and from like preserving high-level information about data types that may have like value semantics, referring to transparency, etc. These are independent properties, independent of the hardware. If you take the user perspective, yes, you want to build a flow. So at some point, there is a model that you are going to, of the hardware that you are going to try to adapt to, but that's mostly, I would say, it's just one concern that you have to deal with. For example, if you're doing graph level transformations, fusion, tiling, etc., you don't have to know much about whether it's a GPU or TPU or whatever accelerator from anywhere, because all these machines, they still have this kind of tile architecture with local memories that are partitions, that are small, different ways of doing data transfer synchronously or not. And the hierarchy of computational and memory structures is kind of similar at the high level of abstraction. So you don't need to know more than that. And this is definitely not von Neumann, by the way, because it's hierarchical. If you're doing backend code generation, and we don't have any MLIR backend publicly, like for assembly language, publicly available as far as I know, but there are some that exist publicly, but without the code. Then you may want to have instruction schedulers, register allocation, all that stuff for a very specific machine using MLIR, and that's possible. But that's just going to build on the backbone of the framework, not necessarily be visible from other users of MLIR. You see what I mean? So you can redo LLVM in MLIR. It's just a dialect. Okay? You can have passes in LLVM ported to MLIR. In the worst case, you just strip the prefix and back syntactically. You can do more than that because you have, of course, builders, etc., that make the API compose as well. But you don't have to see MLIR through the prism of what LLVM does. It's just one possible way of using it. Now, if your question is about machine descriptions, how do you represent hardware for building flows that target a specific hardware and co-design and all that stuff? There was a great presentation at the workshop. I forgot from whom. I think I get from yes, exactly from Xilinx, from AMD, and there are people in the room who are much more competent than I am. I don't know yet exactly how beneficial it is, so ask them.
Okay, thank you.
Okay, so are there more questions? Otherwise, in the interest of time, I will probably just go through these 4 principles of how to get peak performance and peak performance portability, and then conclude. So I mentioned one challenge earlier where we kind of failed. I think it's also not very clear whether MLIR has succeeded in terms of delivering actual performance. So if you care about performance, it can be multiple things. It can be you care about getting speed ups compared to your neighbor, fine, get papers published, etc. Optimization levels, -04, fast, etc. In this particular case, I don't care about that. I care about peak performance. So do we get the best possible performance that somebody with infinite time would have obtained from that particular target machine or system, which is not well defined. But you can, in some simple computations like matrix product, you can define it in terms of flops and peak memory bandwidth and these type of things. But in some other cases, it's more difficult to define. So the main problem is that this is not what compilers are typically engineered for. Okay? The most compilers are defined for the common case. Just like computer architecture for general purpose processors, they are engineered for the common case. Except that the common case is not enough when you care about HPC. I'm not talking about you right here. So if you care about peak performance, you need to address velocity issues. So convince people doing things by hand or semi-automatically with custom frameworks like template metaprogramming for the Eigen library or the Boost library, etc. That it's worth investing into some more generic, more powerful infrastructure that they have to learn, that may miss some essential components, that may apparently make things a little bit artificially complex. And why would they go through that kind of common infrastructure? Why would it be beneficial? And I think that's where we have failed, definitely. Historically, not only MLIR, other approaches before, we have failed to demonstrate that general purpose infrastructure for accelerating compiler research and software engineering has not really made its way into very specific performance-oriented code generators or libraries. The main reason is that performance is not there. Or if it's there, it's not easy enough to get there. So you can use it, but it's more like considered as a heroic effort. Like polyhedral compilers, for example, have been showing absolutely wonderful results compared to what Intel engineers have done, NVIDIA engineers, etc., over the years, but only at the cost of having 2-3 people in the world capable of doing it. So what's the point? I'm not saying it's bad. I'm just saying the demonstration is not made that it's a winning strategy. And maybe there is a bit of a problem redefinition going on here. So I mentioned velocity is really the point. I mean, the adoption of those techniques is a problem. Probably what we need is to redefine performance, like peak performance and peak performance portability in particular. So what we try to do is not necessarily replace one black box by another black box. Like, okay, cuDNN is not the compiler, it's just a library. So can we make a compiler that will replace cuDNN? No, that's not what we're trying to do. What we're trying to do is to understand what performance engineers go through when they want to get the best performance in ML or in HPC, whatever domain. Typically, what they do is some semi-automatic optimization. So they write code and then they try to automate the exploration of different parameters for their code, like tile sizes, etc. And by doing that, they typically reinvent the wheel. Or they use a framework like TVM or Halide, where you have some kind of scheduling language, which is a way to meta-program those transformations more or less in a more or less composable way. And then on top of that, they do auto-tuning, auto-scheduling too, because all these manual things, they are great, but okay, some of it is very repetitive and the search space can be large. And some people go even beyond that, but it's really research is saying, okay, I don't want to write pilot passes anymore. I don't want to write code generation sketches or schedules anymore. I want to do program synthesis. So you have a spec. You have, a spec for the algorithm you want to optimize, a spec for the machine you're targeting, and figure it out. Okay, different ways. For example, you can do differentiable optimizations. You can make the optimization a differentiable process to automatically match assembly instructions with a given computational spec. You can do reinforcement learning. You can do meta heuristics of organ. And this is, I think, what we should keep in mind as the recipe for performance portability. It's not just replacing one black box by another. Is how do we help people doing exactly that? The goal is helping those people. It's not just saying, yes, we can do it. And then I want to mention 4 strategies on how to do that, more like call for help, basically. Maybe you heard about something called PALAS, which is kind of custom operation extension of JAX. Certainly you heard about Triton. if you do high performance computing on GPU in Python. So these are kind of, they call it tiled array programming in Python. Not functional at all. It's just like buffered side effects, but it's embedded into Triton and into the ML frameworks in a kind of seamless way. So you can write operations that are either the normal NumPy operations, or you can write your own operations using iterators, conversions between like value tensors and buffers, etc. in those languages. And Palace is kind of the more functional style integration of side effecting computations in JAX. So the interface remains JAX friendly with transformations, it's value based, etc. But internally you can have side effects. And then the other approach that has been very popular over the years is microkernels. So you say, okay, compilers are great at doing things at high level, but they are very bad at doing fine-grained super optimization, instruction scheduling, the last mile of vectorization, like vector instruction mix, etc. So you can do super optimization, you can do even handwriting of assembly code, whatever, for these black box microkernels. Think of basic blocks that super optimize for one particular shape or one particular operation. And by combining the two, people have gotten actually a lot of success. So you can do high-level array programming on one side, and at the fine grain integrate these building blocks that are completely custom, maybe automatically generated, maybe not. The problem with these approaches is it doesn't compose very well with the rest of the framework. So people write custom code at both levels, like array level and assembly level, and you expect you're going to reuse much of what MLIR provides or what the framework like JAX or PyTorch provide, but it's not just as smooth because you have been writing custom code in the first place. So what would be great is to understand how these things get generated or what tricks people play at in array languages that a compiler flow more traditionally built of like incrementally refining the abstractions, etc., could just reproduce. Yes, but we have to learn from the practice. Let's understand what the experts do. The other direction is make things controllable. So it's kind of redundant with the scheduling aspect of the previous slide. So of the 2 slides back, the question is making numerical computations meta-programmable from the start. So instead of saying I have just tensor operations, talking about numerical computations here because this is about peak performance, but whatever, you could apply that to another domain. Just make it easy for someone else, like a performance engineer, to look at your code and apply transformations to it. So you need some kind of mechanism to assign handles to your values, to your operations. And then on top of those handles, you can say, oh, I want to tile that in a particular way. I want to fuse those 2 operations in a particular way. So you expose the numerical computation to a scheduling interface, through a scheduling interface, so that people can actually implement those transformations. So TVM and Halide are typically successful in that space. I think we can do much more than that. For example, there was a presentation again last week. Told you should not be there, it should be the dev meeting, by a student who was an intern with us, Martin Lucke, who has been working on extending the MLIR transform dialect, some kind of rewrite system, generic rewrite system in MLIR, in the IR itself, but exposing it to Python users. There is also a tutorial by Alex on the transform dialect, which I strongly recommend to watch if you are interested in investing seriously into MLIR. And I think, yeah, if you want to do autotuning research, ML-driven compilation, this is again a great entry point. So you cannot necessarily look at starting everything from scratch, but look at those scheduling languages as an intermediate step. If you want to define your new flow for refining given tensor operations to given hardware, maybe what you're doing is sufficiently similar to what other people have done, except you want to tune the transformations in slightly different. And then quickly, the last 2 directions I would say is make things more like separation of concept. You want to compose generic operations that MLIR is great for with many different type systems, and which MLIR is not that great for, I would say. So MLIR still has, although I try to influence things in a slightly different direction at the beginning, but still has a notion of a main type, basically for every value. And it has attributes, but these attributes are attached to operations, not to values. In general, what you would like to have is a superposition of type systems that capture the different constants you're dealing with. For example, if you're interested in sparsity, like this slide, you want to say, I want to represent graphs using sparse matrices or mixture of experts. If you don't know, no problem, that's not very important, but just different types, families of neural network models. You typically get into like block sparse representations, block sparse matrices. What's the data type for that? You can come up with many different representations, many different abstractions for block sparsity, but how do you compose everything that exists in MLIR or in a given compiler with this new type? You don't want to just forget about floats, about like FP16, ints, whatever, array, vectors, etc. But on top of those data types, you want yet another type system which tells about the representation itself, or the layout, or how this data is being organized. And this is something that we can do. So there is an MLIR sparse compiler that does some of this, but it's using a lot of attributes and metadata. I would say that's not ideal in terms of software engineering. So maybe we can even evolve MLIR further into supporting multiple type systems superposed to the same compilation unit. And you can do all kinds of things like cost modeling, fine-grained pipelining, custom scheduling, like what I was saying earlier, but in a way that composes with different type systems. Like you can have a schedule for matrix multiplication on int8, another schedule for matrix multiplication on FP16, etc. And all this stuff is going to be ideally supported by the same code. You don't have to re-implement it. I don't know how to do that. I mean, MLIR is a good project, progress in that direction, but it's not yet finalized. And then the fourth part, I don't have time to go into any details because I don't have time, but also because I don't know how to do it. So I just want to highlight, I mentioned we don't want to replace numerical libraries with automatically generated black boxes, but we'd like to get rid of this concept of libraries once and for all. So maybe some of you already heard that presentation, but the goal is to say, yes, we have great tools to automate the generation of code, but what we don't know yet is how do we completely isolate the performance engineers from having to shop in a supermarket of numerical functions that are meant to run efficiently. I think this is traditionally how people do things in HPC. You have bottom-up approach. I know how to do MATLAB, great. I know how to do softmax, reduction, collectives, etc. But we'd like to think of this problem more top-down, by essentially as a synthesis problem, saying I'd like to generate the code that runs fast because I know how to do it, but only the code that makes sense for my particular example, not just hope that somebody has done it before and it kind of matches what I'm doing. And I'm skipping all that part on structured operations because you can find the information on any MLIR website. But I would say, okay, it's probably time to really think of not using libraries anymore and saying that all the specialization that we need, we know how to do it. We have compiler frameworks to actually do that. I'm talking about that from the very beginning. What we need is some kind of way to steer this specialization, to steer the production of very high performance code in a way that's going to be just as high performing as numerical libraries, but do it in a demand-driven, like top-down fashion. And so this is probably an uphill battle because some people have tried to retire things that work before. So there was a retire Fortran debate at the time of data flow languages. So Stefan will remember that among others. So it was all about Sisal at the time, like functional arrays, etc. I've been there before. Okay, even though the LLML was involved, so like serious people, not just academics. I'm afraid Fortran is still there. It's called C++ now. And also C++ will retire. There's a clock that counts down, but for some time it's now heavily in the negative land. So it's not retired. So we are probably lost, but let me try still. So numerical libraries have been there forever, like the BLAST. What can we do? I think the direction is probably in the space of some kind of multi-criteria optimization problem. Instead of defining, I mentioned HLO as a list of 100+ operations that everybody should play with, and XLA is going to optimize for you as a black box. You open the box and say, okay, maybe we're going to have tens of thousands or even more so-called primitive operations, but they are not primitive. They are synthesized operations that match the goals, the needs of a given domain, of a given set of like array shapes, just thinking of tensor algebra for now. And you're going to have a kind of dynamic interpreter running on top of this library of so-called tile level operations. So there are two ideas there. One is This is going to be synthesized, so we can do many more ops. We're not going to limit ourselves to just 100. And this is not going to be full tensor operations. It's going to be just tile level. Why tile level? Because that's the last level where compilers really matter. Intuitively, if you do backend stuff, you know, yeah, register usage and instruction scheduling, there is no way out. It has to be a compiler. Somebody has to generate code. But for high-level orchestration of MPI function calls, who cares about the compiler? Most likely, an interpreter can do just the same. You need a plan. You need to exactly know what to do. You need a schedule. You need some communication efficient algorithms, etc., on top of your MPI library. But you don't care whether this is actually completely statically scheduled in a basic block. It doesn't make any sense because there is no like dispatch overhead to deal with. At the instruction level, at the register level, you need instructions and registers. You're not going to just call a function for every hardware instruction. So the boundary, I would say, is typically at the tile level, whatever it means. On the CPU can be like L1 tile. As long as you fit within one core of an x86 CPU, this is like a good level of a good boundary between compiler stuff and let's say interpreted stuff. On the GPU, it may be like warp level, maybe block level, whatever. It may depend a little bit. That boundary may move a bit, but it's important that you don't move above that level. Otherwise, it doesn't make any sense to do compiler code generation stuff. Of course, yes, you do compiler stuff in a different mode, like these transformations I was talking about, automatic differentiation, type checking, verification, etc. That makes sense. But in terms of code generation, it doesn't make sense. And then there is an interesting trade-off, which is how many operations you need to cover just one application, multiple applications, a given domain of applications, and how are you going to make it the most possible efficient design of this space of tile-level operation. So it's a co-design problem, and it's multi-criteria, actually 3 criteria: performance, diversity, so what applications you want to target, and a code size. You don't want to generate 1 billion different lines. And I don't know how to do it, but we did some work together with INRIA Grenoble folks. So Nicolas Tolina's thesis at the microkernel level. So it's exploring basically the space of microkernels, like basic blocks for unrolled loops of fixed shape, which ones run well on a state-of-the-art x86 processors. And in this case, maybe some of you know that like the Bliss library or the math library, like MKL, they typically use 2 or 3 different microkernels at fine grain for different sizes of matrix products. But in fact, there are about 30 or 40 variants that are potentially interesting. And the great thing is that these different microkernel variants, they have different shapes because they have different unroll degrees. They have different vectorization degrees, etc. And having more diversity make it possible to assemble these microkernels in a more like creative way. It's not just like fixed style shape for everything. Depending on the size of the problem, you can compose and assemble these microkernels differently. This is just an example where you know that 128 is actually 12 times 6 plus 8 times 7. And 6 and 7 happens to be pretty good sizes for one of the dimensions of the matrix product, like auto product actually, at the core of the matrix product computation. And if you combine like some hybrid of the two, you cover the space, you cover that particular shape better than, for example, using control flow at the end of a loop, or padding or masking or all kinds of tricks that people do. So that's an example showing that, yes, you can actually have tile-level operations, in this case, microkernels and just like a couple of loops around them, that compose and deliver even better performance than having kind of predefined code generation schemes. So, but that's just an early experiment showing that this direction has value. You have to set the boundary right. And that's it. So there are challenges, yes. Just to recap, what I'd like to do here is that we have a great framework called MLIR. It's extensible. You can do everything with it and nothing at all, but also something. I've listed a few real projects. What matters is controllability. I mentioned coding languages, the transform dialect, I mentioned it quickly. You don't want to just build a black box, just yet another compiler flow. You want to retain the ability to change your mind, to redesign your compiler, etc. In research is great. So I think that's the main reason MLIR is great for research, is because it gives you control on what you want to do. And you need ML. Okay, so people do auto-tuning. That's probably the deux chevaux originally, and much more than that. Not only auto-tuning, also like ML at the core of the compiler heuristics is really there. It exists. It's in LLVM, and it's going to come in many other projects. And thank you.
Is there any question? I take a couple still.
Any questions online?
We got a question in text by Stefan Letz. What do you think about the Mojo language initiative?
I'm not authorized to say. No, that's too easy. I mean, that's correct. I should not say anything in this. They are friends and competitors. So Mojo, I don't know if anyone knows what this is. It's, I don't know what it is actually, because it's both Python and Rust and efficient array programming in a memory safe way, in a Python compatible way, and targeting both accelerators and CPUs, and offered to you by Modular. And you have a binary package that you can download and test, but it's not open source, and it's built on a MLIR. That's within the definition. So what do I think about it? I think it's absolutely amazing that people trying to solve, because that's what they presented last week as well. So people trying to solve performance problems in memory safe languages. In that case, they looked into Rust, figured out that one, it can be done. And second, it can be done in a Python friendly way. Like for Python programmers and Python frameworks, it's possible to kind of have both at the same time. At least some level of this is possible. They have all the kind of flexibility of Python code injection, etc. And you have all the performance and memory safety of Rust. And you have numerical computation on arrays. And you can write this array code I mentioned, Palace earlier, and Triton. You can have this array time-intensive code in the same language. So it's memory safe array programming in Python. Whether it really works, to what extent it can be done, etc., I don't want to say anything. I just don't know. But it's an amazing experiment. Yes. And it's based on MLIR, so if it was open source, it would be great.